Good afternoon, Dr. Stone. Good afternoon, colleagues. My name is Paul Adu from the Department of Mathematics, University of Cape Coast. My presentation is captioned "A Novel Fractional-Order Stochastic Epidemic Model to Analyze the Role of Media Awareness in the Spread of Conjunctivitis." Now, this will be the outline of my presentation: introduction, motivation and importance of this study, limitation and research gap, model formulation, deterministic model analysis, threshold dynamics and stability, properties, fractional order stochastic model extension, numerical methods and simulation results, sensitivity analysis of media awareness, conclusion remarks, and public health implication. Introduction. Conjunctivitis is a highly contagious disease with important public health implication. Smith et al., 2021. Mathematical modeling is used to study the transmission dynamics in the population. Brewer and Castillo, 2012. Media awareness is significantly influenced behavioral response, such as social distancing. Tichel et al., 2011. A media-aware compartment model is proposed to capture the effects. Sumi et al., 2020. The Atangana-Belloni fractional order derivative account for memory effects in disease spread. Atangana and Belloni, 2016. Stochastic perturbations are incorporated to reflect environmental uncertainty. Mayo, 2007. And the research gap, existing literature often fails to combine media info-induced awareness with environmental noise in a single fractional framework. Samuel et al., 2020. These people address these gaps by formulating a novel ABC fractional order integrating media awareness, population framework. The research utilizes a 5-compartment framework to model the spread of conjunctivitis under the influence of media awareness. The population is divided into aware, susceptible, S sub A, then unaware, susceptible, S sub U, infected, I sub A, and recovery R individuals, alongside a media density variable M. Fractional framework. The dynamics are governed by ABC operator that is representing the Atanga-Belloni fractional derivative in the capital sense. The transition of individual from the unaware to the aware class is modeled by the term omega M S sub U. The model incorporates a saturated reversion rate from the aware to the unaware class, defined as beta 2 S sub A or on 1 plus M. Infection rates. Transmission occurs through a bilinear incidence rate between unaware, susceptible, and infected individuals, expressed as B1 S sub U, I sub A. They have contributed behavioral changes, reduce the infected population at a rate RM I sub A, based on a source term theta. growth due to infection prevalence, that is rho I sub A, and the decay rate eta M. Now let's look at the compartmental model diagram. Over here, the population is divided into two categories. We have unaware susceptible population and aware susceptible population. Of unaware class at a rate of A. Then from here, they move to the susceptible aware class at a rate of omega M X sub U due to media campaigns, or the fact that people have had information about the outbreak of the disease. Therefore, they move from unaware to the aware class. However, awareness is not permanent. It may be due to decay or loss of memory or forgetfulness. Others move back, revert to the unaware class at a rate of beta 2 sub A, all divided by 1 plus M. Now, in the aware class compartment, others leave the compartment through natural death. That means S sub A. Also, those who are not aware, when they come into contact with those who have been infected or those who have the disease, they move to the infected class, I sub A. In that compartment, because of the infection, some may leave the compartment to natural death, meaning I sub A. However, others will move to the recovery compartment at the rate of new I sub A. And from the same compartment of infection class, others will leave with the rate of RM I sub A due to media intensity or media campaigns. They will move from that compartment. Even at the recovery compartment, it's possible others will leave to natural death. The media too play a longer role, or a very vital role here. Generation rate is theta. Then the media rate is also rho I sub A. Now look at the state variables and model parameters. As I've explained already, S sub U, S sub A, I sub A, R, M, the A recruitment rate, beta 1, beta 2, beta 1 transmission rate for unaware susceptible, beta 2 transmission rate for unaware susceptible. Then mu is the natural death rate, omega rate of awareness spread from media, nu recovery rate of infected individuals, theta baseline media generation rate, rho media generation rate per infected. And then the alpha is the fractional order derivative. Now this is the complete fractional order derivative in the deterministic sense. So these are the equations for susceptible unaware, susceptible aware, infected class, and then recovery class, and the media. The model is subject to the following initial conditions, where alpha belongs to the interval, open and close interval 0, 1, and all parameters are non-negative. So let's prove the positivity and boundedness of the solution, because we just stated that all parameters are non-negative. However, population cannot grow beyond some bounds. So we need to show how these state variables are non-negative and how they are bound. So the theorem 1 states that the set C is given to us by the equation then is positively invariant with respect to the model 1. We define total population as n of t, that we add s sub u of t plus s sub a of t plus ia of t plus r. Summing the first 4 equations, if sum all the equations, some terms will cancel out. So we will end with a minus mu into s sub u plus s sub a plus I sub a plus r. But we know that s sub u plus s sub a plus I sub a plus r is the sum of total population is n of t. So this sum become a minus mu n of t. Now we have to apply Laplace transform to this equation that we are having, and also use the properties of Atangana-Belloni derivative in the capital sense. So that equation becomes the total population is equal to A on S mu plus N into brackets NO minus A on mu, bracket closed. Then we have S exponent alpha minus 1 divided by S exponent alpha plus lambda, where lambda is constant related to the ABC operator parameter, and therefore it's mu. Now, when we take the inverse Laplace transform, the solution for total population is now given as that n of t is equal to A on mu plus into bracket n of O minus A on mu bracket close multiplied by E sub alpha into minus lambda t exponent alpha, where E sub alpha denotes the one parameter Mertang-Leffler function. Now that function, if you look at Mertang-Leffler function, the asymptotic nature of that function says that as t approaches infinity, E sub a of minus lambda t exponent alpha approach 0 for all t greater than 0. So when this is evoked or when this is applied to the equation, it becomes very clear that we are going to live with limit as t approaches infinity, n of t will be less or equal to A on mu. And this is the bound of the total population. Now, if you look at the media also, with the same argument and the same approach as we use for total population, we define our equation with the inverse of the Laplace transform. M of t will be equal to theta plus rho I sub a all on eta plus m of O minus theta plus rho I sub a or on eta multiplied by E sub alpha minus eta first derivative of eta t exponent alpha. And when you also take the same Laplace asymptotic nature of it, you say that as E sub a into minus n eta prime t exponent alpha will be approaching 0 as t is approaching infinity. So when that happens, all the term on the right-hand side of the equation, the second term on the right hand of the equation, go to 0. So we are left with m of t less or equal to, because less or equal to because it was equals and some part of the equation of other side had gone to 0. So it will be the rest will be the other left or equal to m of t. And that's the bound of the media. Now let's verify non-negativity of the state variables. We examine the vector field of the boundary. So for S sub u is equal to 0, we are going to have here S sub u giving us a plus beta 2 S sub a, all divided by 1 plus m, and this is greater than 0. So that is positive. For S sub a equal to 0, then we have omega m S sub u also greater or equal to 0. Now for I sub a, they're going to have 0. Because when I is 0, the whole thing will tend to 0. And then for m, when m is 0, you're going to have m is equal to theta plus rho I sub a, also greater than 0. So this shows that solution with non-negativity initial condition remains in the positive R exponent 5. So it means positive. Now you look at this free equilibrium of the system. The zero equilibrium epsilon 1 is the state of the system where the infection is absent, where there's no infection. Then when you set the fractional derivative to 0, when there's no infection, then the equations, we can set it to 0. By definition, the infectious population at disease-free equilibrium is equal to 0. When you put in the values to the disease-free equilibrium equation, it will give you 0. Substituting this into awareness dynamics. So you put this one into the media equation, and you're going to have theta plus rho I sub a minus eta m equals 0, giving us m at disease-free equal to theta on eta. So the disease-free m will be equal to theta on eta. Now, when you set the two equations, that the susceptible unaware and that of the susceptible aware, we set them to 0. And we can express susceptible aware at disease-free in terms of that of unaware at disease-free. We are just writing S of so we are going to have this equation here. So now, when we sum the equations for S sub u at disease-free and S sub a at disease-free, this is what you are going to have. You're going to have a minus mu S sub u at disease-free minus mu S sub a at disease-free. And that is also equal to 0. So you're going to have a is equal to mu into S sub u at disease-free plus S sub a at disease-free. Of course, we have answer for S sub a at disease-free. So this substitution to that is what you are going to get as our equation. So we have a is equal to mu into that. That will give us mu S sub u at disease-free multiplied by what's in the bracket there. Now solving for susceptible unaware disease-free and that of aware disease-free. Now we know our m at disease-free is equal to theta on eta. And then our I2 is equal to 0. So we do substitution to the final equation you have there. You're going to have S sub u at disease-free is equal to that function here, or that equation here. Now that of x sub a at disease-free is also equal to this equation. So disease-free equilibrium, this is what we have. The first term here represents susceptible unaware at disease-free. The second one represents susceptible aware at disease-free. Of course, infection class at disease-free is 0, and the media density at disease-free is theta on eta. Now you look at the basic production number for the deterministic sense. They define the average number of secondary infections produced by a single infected individuals. Now, the key points here is that you need to realize the infection system at disease-free equilibrium. So we identify the infection class with its equation, and that's the infection class that we have here. So we decompose into new infection F and transfers V. So if you look at the equation for infection class, for the new infection denoted as F, it is the B1, beta 1 F sub U I sub A. And for the transfer denoted as V, it is a nu plus mu multiplied by I sub A plus Rm I sub A. So if we want to compute our Jacobian matrix, let's compute our Jacobian matrix. So we know our F, we know our V. So we have to find partial derivative with respect to I sub A. Then evaluate it at disease-free equilibrium, where M at disease-free equilibrium is theta on eta. So when you find the partial derivative of F with respect to I sub A at disease-free equilibrium, we are going to have beta 1 S sub U at disease-free equilibrium. Then for V, partial derivative of V with respect to Im at disease-free equilibrium, I'm also going to have nu plus mu in brackets plus Rm at disease-free But you know our M, so just do substitution into this, and then you see what happens here. Now, our next generation matrix is going to be F times the inverse of V. But in our case, it's a scalar. Our matrix is a scalar. So our V inverse is given by eta into nu plus mu plus R theta. R theta is there because we have substituted the value of M at disease-free. Now, when we multiply the inverse of V by F, we are now going to have beta 1 S sub U at disease-free eta, all divided by eta into nu plus mu plus R theta. Now, the basic reproduction number is the spectral radius of that. Substituting the previous derivative of X sub U at disease-free, we obtain, if you look at the final answer for F times V inverse, there's an element of S sub U at disease-free. So you need to substitute the value of that figure into the equation. When we do that, finally, this becomes our reproductive number, R naught, for deterministic sense. Now you look at the local stability of the disease-free equilibrium. And the theorem states that the disease-free equilibrium, epsilon 1, is locally asymptotic stable if R naught is less than 1, and unstable if R naught is greater than 1. So we want to verify whether the disease-free equilibrium is locally asymptotically stable or not. We're able to show that our R naught is less than 1. It means it's locally asymptotically stable. Otherwise, it is not stable. Now you have to find our Jacobian matrix so that we can go ahead and solve for it. Now, Jacobian matrix, we need to show, or we need to verify these entries. And evaluate it at disease-free equilibrium, where I sub A is equal to 0, M at disease-free is theta on eta. So when you do the evaluation at disease-free equilibrium, this will be our matrix. But let me quickly glance through, let me quickly see how Jacobian matrix is obtained. Now we just find the partial derivative of the system. So if I let the first equation of deterministic equal maybe F1, then I'll differentiate partial derivative of F1 with respect to that of X sub U. And that will give us minus into bracket omega m plus mu. That's the first entry here. When you continue with that, that's A11. For A12, we differentiate the first equation, that is S sub U equation, with respect to S sub A, with respect to S sub A. And when you do that, that differential will also give us beta 2 on 1 plus m. Maybe A13, that the third entry is here. You do the same thing, differential of f of 1, which is the equation for S sub U, respect to partial differential of I sub A, will lead us to negative beta 1 SU. So that's the process to get the Jacobian and get the answers here. Now, when this Jacobian is evaluated at its free equilibrium, then this is the answer. Jacobian is free equilibrium is equal to this. Another difference here is that all the state variables here will be evaluated at its free equilibrium. So the first entry becomes omega m, this is free equilibrium plus mu, and the rest will show that this is free equilibrium. However, when you do that for A23, our results will now become minus into bracket 1 minus R sub 0. That is the productive number. That will be difference that we can see here. Because when you do that, that's what the results are going to get. Now let's look at this. Now, after getting a Jacobian matrix, as in this, you can see that these are in blocks. When I take the last block here to my right and find the eigenvalues, you see that you're going to have lambda 1. The lambda 1 is the median eigenvalues. The lambda 2 here is also going to be the affected eigenvalues here. So if you find the eigenvalues, notice that lambda 1 is going to be minus eta, which is less than 0. And then when you take the lambda 2 is equal to R sub O minus 1. Now, when R is the productive number, R sub O, is less than 1, then you put here, notice that lambda 2 also be less than 0. Now we are left with other 2 by 2 susceptible block in them. The block here, this block here is this block here that we want to find is lambda, or these eigenvalues. So you want to use lambda 3, lambda 4 for the eigenvalues. Now use the trace. The trace of that susceptible class, the 2 susceptible class, will be minus this. I mean, the trace is the sum of the leading diagonals. So we sum, we're going to get negative of this. It's less than 0. You find the determinant of the same susceptible class. Determinant 2 will be greater than 0. Now, since the trace is less than 0, determinant is greater than 0, it means that lambda 3 and lambda 4 have negative real parts. So you have shown that, so for fractional order system with alpha into this, or alpha belongs to this interval, the equilibrium is locally asymptotically stable if all eigenvalues satisfy this condition. And once we have seen and showed that all the eigenvalues are negative, have negative real parts, when R is less than 1, they lie in the stable region of the complex plane for any alpha belonging to this interval. So that shows that indeed all these things are also in that interval. And that means that it is locally asymptotically stable for this free. Now we move on to local stability at endemic equilibrium. We also found out that what about endemic equilibrium? Would the system be stable or not? To analyze the local stability of the endemic equilibrium, given by that, we linearize the system using the Jacobian matrix. Once again, the Jacobian matrix will be used. And I've rewritten the system as F1, F2, F3, F4, written the system to help us able to take partial derivative as we have done already. So this is our Jacobian that we're going to have. We take the partial derivative. Some terms or some entries will be 0. So we have 2, 3 being 0, 3, 2 being 0, 4, 1, 4, 2 being 0. And the values of, or the answers for A, 1, 1 is given here. The answer for A, 2, 2, all the answers here have been given to us. Now, what you need to do is that you need to verify this. You need to verify this coefficient of our characteristics equation from the Jacobian matrix. It's given to a lambda exponent 4 plus alpha 1 lambda exponent 3 plus alpha 2 lambda exponent 2 plus alpha 3 lambda plus alpha 4 equals 0. So you need to define, you need to verify, you need to find out the answers of alpha 1, alpha 2, alpha 3, alpha 4, and determine their nature. So for alpha 1, the negative trace of our Jacobian. This is a Jacobian negative trace that you sum all the leading diagonals here and negate it. And that's what our answer alpha 1 is telling us. So for alpha 2, let me move on to the next slide and show how the alpha 2 is obtained. Now the coefficient of alpha 2 is the sum of the following 6 principal minors of Jacobian at endemic equilibrium. Now the alpha 2 is going to be the sum of all principal minor of the system of order 2. So what it is that we first of all pick M11 means that you're talking about first row, second row, first column, second column. And when we do that, this is the resulting matrix you're going to have, and this is its determinant. M13, we are talking about the first row, third row, first column, third column. When you do that, this is the matrix that you're having. And this will be the answer for its determinant. We have M14, that is the first row, fourth row, the same with first column, fourth column. Then you take that, this is the resulting matrix, and its determinant is going to give you this. M23, that's the second row, third row, second column, third column. When you do that, this is the resulting matrix, and this is determinant. M24 represents the second row, the fourth row, as against second column, fourth column. And this is the resulting matrix you're going to have. And this is its determinant. Then M34, third row, fourth row, against third column, fourth column. The resulting matrix is this. This is the answer for its determinant. So the alpha 2 is the summation of all these 6 principal minus submatrices, all the determinants here. So it's equal to M12 plus M13 plus M14 plus M23 plus M24 plus M34. That's the how we obtain the alpha 2. So we sum all these answers that we obtain here, it will be equal to the answer that I have shown in the previous matrix. Now, we need to also find the principal minor of order 3. And that will be the coefficient of alpha 3. So it's the negative sum of 3 by 3 matrices of principal minus. So for first matrix M1, what you do here is that you take row 1, column 1, the resulting matrix is this. Then you find the determinant, you're going to have this. M2, you take row 2, column 2, and then the resulting matrix is this. Determinant will give you the answer that we have here. Then we have M3 representing third row, third column. We take that one out. The resulting matrix will be this, and that will be the answer that we are having. M4 also represents fourth row, fourth column. When you take that one, cross that one out, this matrix will be the resulting matrix, and it is determinant. So alpha 3 to the negative sum of all the 3 by 3 principal minus from the system. So alpha 3 will be given to us as negative into M1 plus M2 plus M3 plus M4. That will be the answer when you get the answer that the system has given us in the previous slide. Now, we need to also verify how the alpha 4 was obtained. So I'll pick the whole Jacobian matrix because alpha 4 is a 4 by 4 determinant itself. The whole matrix determinant itself. So we pick the whole matrix and see how best we can do that. But because if you look at the matrix very carefully, you notice that the fourth row has 2 zeros. The fourth row has 2 zeros. So it will be easier for us to expand along that line so that you get our answers without sweat or with the shortest possible time. So when you take it from, when I use A43, that the third column here, as I get the fourth row, give the resulting matrix that I'm going to have. Then when I use the A44 point here, that is the fourth column and the fourth row, the resulting matrix also will be this. So what we need to do is that we need to find determinants of these matrices. And whatever I get, we can now sum them. So first of all, we have to find M1, determinant of M1. M1 denotes the first matrix here. This is our M1. So we found the determinant of that, and that will be our answer for M1 matrix, determinant of M1. And the second minor, which is M2. And as we have seen, this is the M2, this will be the M2 or the second minor matrix for the alpha coefficient, alpha 4 coefficient. And when you also take the determinant of that, this will be the answer. So applying row coefficient. Now what you do is that we now multiply, see if you look at this matrix very well, it was minus A43 into that. But the answer we had is only about the determinant of this matrix. So we have to multiply by the answer here. In the same way, M2 the same way. M2 is A4 for multiply the whole matrix here. But we only found the determinant of this matrix. So the answer we have to multiply by A44. And when you do that, this is the resulting answer I'm going to get. So minus A43 multiplied by M1 will give you this. And A4 for multiplied by M2 also give you that. So when you combine the final expression, if you combine the final expression, that we add minus A43 times M1 and then A44 times M2. When you add the resulting values here, then our alpha 4 will give us this answer. And this is exactly what the system is producing for us. So we will show how alpha 4 2 is given. Now for a fractional order system, the endemic equilibrium is locally asymptotically stable if all eigenvalues lambda sub I satisfy this. The argument of lambda I greater or equal to alpha pi on 2. Now when alpha is equal to 1, this reduces to classical Routh-Howitz condition. Classical Routh-Howitz condition. And it is not going to be easy if you want to solve the system analytically. So this will help us determine the nature of alpha 1, alpha 2, alpha 3. And that's condition, or that's root Harriet condition states that alpha 1 is alpha 1 greater than 0, alpha 2 greater than 0, alpha 4 greater than 0. Then we have this alpha 1, alpha 2, alpha 3 greater than alpha 3 squared plus alpha 1 squared, alpha 4. So what we do here is that we need to verify when these conditions are satisfied, all eigenvalues have negative real parts, ensuring that the system is locally asymptotically stable at endemic equilibrium. Now, when you go back and do substitution, into that, if you take alpha 1, the negative phrase, all the leading diagonals, and we are lucky we have all the entries, the answers there. When you compute it, you notice that alpha 1 greater than 0. You do the same thing for alpha 3 greater than 0, alpha 4 greater than 0. And the last condition here, once alpha 1, alpha 2, alpha 3 greater than alpha 3 squared plus alpha 1 squared, alpha 4, we can easily find our alpha 2. Our alpha 2 be greater than alpha 3 squared plus alpha 1 squared, all divided by alpha 1, then alpha 3. And when you do that, once alpha 2 greater than that term, it means alpha 2 is also greater than 0, because already we have shown that alpha 1 is greater than 0, alpha 3 greater than 0, alpha 4 greater than 0. And these are the terms on the end side here of this inequality. So once alpha 2 greater than those terms here, automatically alpha 2 also greater than 0. So you notice that all this will now ensure that the stability of endemic equilibrium is locally asymptotically stable. Now we move on to our fractional order stochastic model. Fractional order stochastic model. Now we are transitioning from the deterministic framework to a fractional order stochastic model, which accounts for environmental fluctuation affecting disease transmission and population transitions. Now, these are the key notes. Environmental noise include climatic variation, social behavior shift, and volatile media influence. This is the stochastic perturbation incorporated by this or as this, where WT is the standard Brownian motion, and then the sigma here, the stochastic intensity. Fractional calculus at Tangana-Belloni operator retains the memory effect in dynamics. Now, using the Tangana-Belloni operator in the Capito sense, we let GI of t, where I equals 1, 2, 3, 4, up to 5, or the 5 equation, or be independent standard Brownian motion and their intensities. So now the fractional order stochastic model is presented at this, where this part, deterministic part, this is the stochastic intensity. When you talk about this, so this means that this is the stochastic model, an extension of the deterministic model. So we have that one for S of U, S of A, I of A, R, and then the M. This is for numerical schemes. This equation is specially made for numerical schemes. When we talk about that when we get to numerical schemes. Now we look at how we can generate or how we can get the stochastic reproductive number, RS, R naught exponent X. Now that reproductive relation determines disease extension or persistence. The number that we are going to determine, the important is that it determines whether the disease will die out or the disease will persist under random environmental noise. So the stochastic differential equation for infected population, I sub is given by that. This is in stochastic form. Now this term here is the transmission term. This is the total removal term. This is the stochastic part of it. Now you need to employ Lyapunov function, very important. And you also have to use Ito's lemma. So when I apply the Lyapunov function, then I will define my V of A sub A as lane is I sub A. This is the Lyapunov function. Now, when you apply the Ito formula to this function, that is D ln I sub A, the Ito formula will let us have 1 on I sub A F of I sub A minus 1 on 2 I square sub A G square into I sub A plus 1 on I sub A G into I sub A G3 of T. Now, substituting drift and diffusion terms. We do the substitution of drift and diffusion terms. Now, diffusion term, the stochastic part of it, the drift is the deterministic part of it. With this substitution to that, so this F is what we have here. Then the stochastic part also is what you also have there. Now you notice that the I, you can have a cancellation here, the I's here. So substituting drift and diffusion term, we have done that. Yeah, so when you do the cancellations here, you see that you're going to have here this what they call the G here representing the sigma 3 squared on 2. All things will cancel out here to give us this, with the stochastic part also adding to the drift. So now let's look at the growth rate evaluate at disease-free equilibrium. So here we're going to have all the X sub U will be evaluated at disease-free equilibrium. S sub A will do the same thing. MO also be the same thing. And our growth rate here is what you see in the bracket here, that growth rate. So when you do that, you only have good B1X sub U at disease-free plus B2 X sub A at disease-free, all divided by 1 plus M at disease-free, minus the total removal term, and then minus this term also here. Now we divide through, or we divide by the total removal term, and then when we do that, this is what we are going to get here. We're going to get the productive number for stochastic model as B1X sub U at disease-free plus B2 S sub U at disease-free, all divided by 1 plus M at disease-free into the removal term here. And we have the same minus this term also here. Now we can now express the stochastic reproductive number in terms of the deterministic reproductive number, RO. And if you are very critical, when we prove the reproductive number for deterministic, this term here is what represents the deterministic term for reproductive number. So it simply means that when we do that, simply means the first term here, the whole of this term here, the deterministic reproductive number minus. So the stochastic reproductive number will be deterministic minus this term. So that's the answer that we are having here. So for the stochastic reproductive number less than 1, infection dies out almost surely. And then for it greater than 1, infection may persist despite environmental fluctuation. So now that we have this stochastic reproductive number with these conditions, that is less than 1, infection dies out almost everywhere, almost surely. greater than what the infection persists, we can go ahead and look at extinction and that of persistence, because this ratio is going to help us find it. Now, the mean of the ratio quantifies how environmental noise reduces the effective reproduction potential of the disease. Because these are environmental noise, and we are taking it from deterministic reproductive number. So it's reducing it. So the stochastic reproductive number automatically is going to be lesser than that. Okay, let's look at extinction theorem for the stochastic fractional order. We have a theorem here. Now, this is the condition. We state that if the stochastic reproductive number is less than 1, then the infected population IA of T will decrease to 0, almost shown that the disease will die out. So we want to show that this is indeed true. If this is true, then we can conclude that the disease will die out eventually. So this is the term we are going to use here. Okay, so we have to apply Ito's formula to I sub A, the Lyapunov function. So the Lyapunov function, you have seen it already. Do the function, and then we apply the Ito's formula to it. So D of ln I sub A will be equal to this answer here. This answer here. Then simplification of the drift term. The drift term here. Drift term here. This is the fusion term here. We've just simplified the drift term. What it means is that we will just take 1 on I sub A here and multiply it through by that. Multiply it through by that. When you do that, this I will no more be there. This I also go. Then this I will go. So it becomes beta 1 S sub U plus beta 2 X sub A, all divided by 1 plus N minus the removal term here. That is this term here, minus it, then with the stochastic part here. Now, when we integrate and bond it, so we integrate this function here, or this equation, integration is from 0 to t. So we integrate this side with 0 to t. This is our answer we're going to have. And then we also integrate this side from 0 to t. Then when you do the integration, we divide through by t. Integration is divided through by t. So you can see that this is divided by t, and this shows that everything here is divided by t, and then the stochastic time part is also divided by t. Now you look at the feasible region properties. This you want to look at some regions that we can work within. So when you do that, then we can say that the ln A of t or on t is less or equal to, I've just taken this minus ln A of 0 of t to this side, taken to join this, the right hand side of the equation. And once I've taken that to that side, this ln A of t will no more be equal to that. It will rather be less or equal to that. I've taken some aspect of that equation, some terms out. So less or equal to this term here, that's equation number 15. Now this equation number 15, we can evoke the strong law of large numbers for Mittingers. And that says that G3 of t or on t as t approaches infinity will be 0. Promotion. Hence, when you do that for this equation, you do that for this equation number 15, you notice that this term here, the stochastic part here, will go to 0, and that is why you don't see it here anymore. So that term will be 0. Then we are left with ln as t approaches infinity, 1 on t ln I sub A of t less or equal to that. Less or equal to that. Now we divide through by the removal term. we divide through by the removal term. So when you divide through this term by that, you're going to have this less or equal to that multiplied by, we divide here by the same term here, we have 1 plus m at this is 3 times that term here. Divide through by this, we have minus 1. And divide this one and simplify. Divide this one by this term, so we're going to have this answer here. And if you look at this equation very quickly, notice that from this part, that is those in the bigger bracket, it is the same as the reproductive number for the stochastic model minus 1. I'm talking about the whole of this term here. So that's why I say it's equal to the removal term multiplied by the stochastic reproductive number minus 1. Since the reproductive number for the stochastic is less than 1, this ensures that limit of 1 on t ln a of t less or equal to the removal term multiplied by the reproductive number for the stochastic minus 1 is less than 0. Is less than 0. The whole of this term for the bigger bracket is the reproductive number for the stochastic minus 1. And it's less than 0. Because if our R is less than 0, so if I put any number less than 0 here, it will make the whole of this term go to negative, and that will be less than 0, almost surely. So we have shown that the disease will die out. So the extension is proved now. Now let's look at the persistent mean for the stochastic fractional order. The persistent, where the disease will persist. It will not die, but it will persist. So this is our theorem for that, and the infected population is given by this. So if this condition is satisfied, if this condition is true, where gamma is greater than 0 is determined by the system interaction parameters. So what I'm going to do, I want to show that this is true. We want to show that this is true. Then we're able to show that the disease will persist. Now we integrate the arithmetic equation of the stochastic differential equation for infected class. So this is the infected class stochastic differential equation. When I apply Ito's formula, we have used it very well today. We're going to have d of ln A is equal to this. We have seen this here, plus the stochastic term here. We integrate from 0 to t, and this term becomes this. And then the whole of that term to become this. However, when we do the integration, we also divide through by t. Divide through, find every time this is happening, you divide through by t. So when you do that, you're going to have this equation as a result. Now we analyze of the limit term here. Let's analyze the limit term here. If we take ln I sub a of t as divided by t, as t approaching infinity, you're going to get 0. Because when you have a fraction where the denominator is becoming bigger and bigger and bigger, that fraction becomes smaller and be approximated to 0. So that's the implication here. Then we have the same thing here, that also then take the limit of of sigma 3, g3 of t, or on t, as t approaching infinity, also equal to 0, almost sure. The same explanation here, as the denominator become bigger and bigger, the fraction will be closing to 0, close 0. So when you do that, and we linearization around this is free equilibrium. When you do this, taking this limit here, that we now do linearization around this is free equilibrium. Approximate the average of susceptible and media classes. So beta 1, if we could recall here, this has gone to 0, this has gone to 0. So I left with this term here. That's why we have the beta 1 on t, integral of 0 to t su of x dx minus r on t, integral of 0 to t of m of x. Yeah, the beta 1 is a constant, so I can bring out beta 1 on t. T is the denominator, so I can bring beta 1 on t. R2, I can bring it out here. And this approximately B1, beta 1, S sub u at this is free minus Rm at this is free minus gamma into 1 on t, integral 0 to t, I sub a of x dx. Now, when you substitute the answer for R not exponent 5, this is the stochastic reproductive number, and taking t to infinity, this is the resulting equation that we are having. You're going to have 0 less or equal to beta 1 s sub u of this is free minus this removal term, minus this term here. Now, once again, we divide through by the removal term here. So we have here S, we have the removal term multiplied by B1S sub u of this is free divided by the removal term minus 1, because when you divide this one by itself, we're going to get minus 1 here. Then this one, we have mu 3 squared, all divided by that, because you divide through the 2 multiply this term here to give you this answer. The minus limit as t approaches 1 on t, integral of 0 to t, I sub a of x dx. Now, using the definition of the stochastic reproductive number, so the reproductive number, we notice, or we have already stated, that if this condition is satisfied, then the disease will persist. Now we divide through by gamma, which is greater than 0. So divide here by gamma to cancel out. Divide here by gamma. What we have here. And you can see that since the stochastic reproductive number is greater than 1, the right-hand side is strictly positive, and the infection population persists in mean almost everywhere. While this side is positive, it means that it's greater than 0. And when that is done, we are going to say that, or it means that the infected population persists in mean almost sure. So we also show persistence in this context. Now we are looking at some of the diagrams and interpretation now. So let's look at figure 2. Figure 2, because the other figures that we have already, therefore, we can't start from figure 1. So we have figure 2 here. Now with the figure 2, this, we can notice that endemic equilibrium. Figure 2, the trajectories of population for fractional order. For alpha is equal to 0.90, alpha equals 0.95, and alpha is equal to 1. So for A, when we take alpha is equal to 1, this is the alpha is equal to 1 line here. Alpha is equal to 0.95. That's what also we have here. And then alpha is equal to 0.90 on the line here. You notice that when the alpha value is higher, alpha value is higher, the value, it increases the value here. We increase the value here. So for B part of the figure, also you are using the same alpha 0.90, 0.95 and that. Now, if you look at the diagram here, when alpha is 1.0, look at the line for the green line, the alpha 1.0, while the blue is meant for alpha 9.5, and the red is meant for alpha 9.0. And for the C2, you have the same interpretation then. When alpha 1, alpha is 1, then you notice that that's the green line here. No, that is this line there for alpha is equal to 1. Then for the green line, you're talking about alpha equals 0.95. And then for the other line, you're talking about alpha equal to 0.90. So the trajectories of the population here is that the equilibrium exists in the system and is locally asymptotically stable. Asymptotically stable. You notice that it is asymptotically stable because if you look at the lines here, you notice that the system is close to this, that asymptotic nature of it, very close to the line here, but asymptotically, it doesn't have to cross it, but very close to it, very close to it. That is locally asymptotic stable. For figure number 3, we have A, we have B, then we have C. But for figure 3C, the contour plots of R0, that the productive number that we have there for various combination of omega and that of theta. Now, notice that the lower the value of omega and theta, the higher the reproductive number. Now, the reproductive number, to the extent that R0 reproductive number is less than 0. So you're saying the higher the combination of omega value, that of the theta value, the higher the reproductive number. So influence of varying omega and theta on R0. When omega and theta increase, the R0 will also increase. That is what we're talking about here. Then let me also talk about variation in system classes. That is figure 5, variation in system classes. And for figure 5, you see that it can be observed that as the omega is increased, the effective population size also decreases. If the omega is increased, the population size decreases. And could control by creating awareness among unaware class. So we are saying that whenever we increase the value of omega, the population number also increased, meaning that when more people become aware, more people will isolate themselves and eventually control the disease that we are talking about now. So that is for, let me pick this one for the stochastic sense. That is figure 7. And I'll talk for A to C, or the A to some of the figures. I'll talk about them. Now, this is trajectory population for fractional order when alpha is 0.20, 0.30, 0.45, 0.50, 0.65, and 0.70. A is meant for susceptible unaware class. B is for susceptible aware class. And if you look at the A, see that's characterized by many infections. You look at the A here. Look at the figure that we have there. But for B, when we increase the value of alpha, fractional order derivative, when we increase it, we increase that fractional order derivative, you notice that we have reduction here. This may be due to individual becoming aware of the disease. When you increase the value, when you increase the alpha value, you see that the disease population with the disease will reduce. And we are saying that this is partly due to the fact that people have become aware of the disease and therefore take precautionary measures like isolation, and that will reduce the number of people with that infection. Now for C, for the figure C, is talking about number of infected individuals, I sub A. And it shows that as the fractional order increases, the count of infected population also rises. This is a clear case of fluctuation due to the randomness with the number of infections that can occur at a given time. So you notice that as the order of alpha or the value of alpha is increasing, the number of infected population too is increasing. And this is a clear case of environmental fluctuation. And so numerical scheme, the simulation utilizes Newton polynomial-based numerical scheme, specifically designed for the Atanga-Belloni fractional order, fractional operator in capital sense. Biological parameters, key rates include the recruitment rate, A 0.5, natural death rate 0.01, the infection rate beta 1 0.2 per day to represent viral transmission. The media awareness effects are governed by the awareness growth rate, rho 0.01, 0.1, the depletion rate, eta, and that is a concern for public consumption for public information. Stochastic variation, randomness in transmission is incorporated using standard Brownian motion. Stochastic constants ranging from 0.01 to 0.1. Now, fractional order impacts. Simulations show that varying the fractional order parameter within this interval significantly alter the peak of infections with lower values capturing memory effects that delay outbreak peak. So the fractional order perform better, as we have explained. Reduction number stability. Numerical results confirm that when the basic reduction number is less than 1, the disease-free equilibrium is locally asymptotically stable. Stochastic extension. High level of white noise as shown to lead to the extinction of the disease even when the deterministic R naught is greater than 1. So you have seen this in the proof. Then the media campaign efficacy. Simulation demonstrates that increasing the media campaign rate, theta, effectively reduces the number of infected individuals, I sub A, and shift the population toward the aware susceptible class, S sub A. And these are some of the references that I have. Thank you. And if there's any question. Thank you, Prof. Doc, and thank you, colleagues.